talk to us about escaping small sets on the Boolean cube and other domains. She's an undergrad here at CMU. So the floor is yours.
Right. Hi everyone. So I'll be talking to you about how to escape small sets on the Boolean cube and some other stuff. So this is my picture of a Boolean cube. I call the Boolean variables -1 and +1, and that's like a high n-dimensional Boolean cube for some high number n, and here's a set inside the Boolean cube. So we can take a random walk on the cube, and we walk around a bit, and each random step we flip one bit of the string that we're on, and that's what we consider neighboring elements of the cube, and we flip some bits and eventually end up outside the cube. So the question is, how long does it take for us to end up outside the set that we started on? And to simplify this question a little bit, instead of saying like how long do we end outside, how long do we take to end outside, we can just ask what's the fraction of edges that cross from inside the set to outside the set. To like talk about this, we make this definition of the conductance or expansion of the set, and that's just the probability that an edge has one side inside the set and one side outside the set conditioned on the one end of the edge being inside. So yeah, I'll explain what this means in pictures. We have a cube here. I'm drawing like the what is this pointer? I'm drawing the zeros at the top and the ones at the bottom, and each level means it's a different Hamming weight, which means the number of ones and zeros inside. And what the conductance means is I'm picking a random point inside the set, and I look at the edges going out of the point, and look at how many of them end up inside the set and how many of them end up outside the set. And I do this for every point in the set and average over them all, and that's the conductance. So in this like high dimensional picture, what the conductance looks like is it's measuring the length of the boundary of the set.
So but A doesn't necessarily have to be connected. You're just sort of drawing it this way for convenience or something.
Yeah, it's just more convenient to draw a connector as well. Yeah. And yeah, so so I'll just go through some examples about what this conductance looks like for various sets. So if we consider like A to be everything, then the conductance is 0 because it can't ever end up outside. If you consider A to be just one point, then you always end up outside, so the conductance is 1. And a more interesting set might be if A is like the indicator set of one variable. So if A is, the string is in the set that the first coordinate is 1, and then you have exactly 1/n chance of ending up outside, because that's the chance that you will randomly flip that bit that A is the indicator of. And so similarly, if we have more than one coordinate that A depends on, then there's like a constant number of times 1/n. That's the conductance. So yeah, in this hook, it's like basically the examples that we want to keep in mind is just A being either one coordinate, A being either just the indicator of one element, or A being being the indicator of one coordinate, which is like half the elements in the set. Alright, so from those examples, we can see that like different sets have many wildly different like conductances, but it could be interesting to ask if we know beforehand what's the volume of the set, do we know something about its conductance? There's like in the examples I showed you that if you only have one element in the set, it has like a super high conductance. But is it possible that you have a constant number of elements in the set, but somehow they are all clustered together in a way that the conductance is very low? And yeah, so this question is really asking whether there's something special about the geometry of the cube that like tells you things about the conductance just based on the volume of the set. Yeah, so to try and answer what this means, we'll first like try generalize the random walk that we're using a little bit. Like the reason why we need to do this is just because if you only take, like the Boolean cube is a bipartite graph. So if you only take one step, then you know, if you only take like an integer number of steps, you know for sure which parity your string is, and that's kind of hard to analyze the mixing of. I just leave that vague for now, but I'll talk about how to generalize this so that it's not, it no longer has this bipartite business. So instead of taking only one step, we can instead consider the case where we split up the time one into delta segments, and at each like time step delta, with probability delta we take a step, and with probability 1 minus delta we do nothing and just stay there. So yeah, and we do this 1 over delta times. So if we take delta to be 1, then this is actually equal to the one-step random walk. So this is like a generalization of what's happening in the one-step case. Yeah, so like on the picture, what it looks like is that we still pick a random point, but now instead of only sampling its direct neighbors, we're going to sample from the entire cube with some like decreasing amount of probability the further away the sample is.
I forgot, what are you trying to maximize the conductance or minimize it?
We're trying to minimize it, yeah.
So if I said, there are n bits, but let's say I pick a subset of k bits, and I take all patterns of those k bits, so I have 2 to the k. Would that be the minimum conductance for 2 to the k?
Wait, sorry, say that again?
I take a subset of k to the bit, the first k bits.
Right.
All combinations of those.
Yeah.
And the other ones are all 0. That's 2 to the k elements.
Sure.
Would that be the minimum conductance for a set of size 2 to the k? Conductance would be, if you change anything in the k, it stays the same in the set. If you change any other one, it goes out of the set. It's
Right.
easy to,
So that should be the minimum for that.
So just more to like minimum conductance, the points should kind of be close to each other in some sense, right?
Right.
Okay.
Yeah, that's true, that's a theorem.
that seems like that should be the minimum
That's like
conductance.
Papa's theorem.
So we've solved it for any power of 2, right? I solved it, I just solved the problem.
Papa solved it before you then.
Right, but okay, so I guess yeah, I'll just like talk about it a little bit more, and we can talk about yeah, there are some other interesting related questions to that as well. So that's like yeah, it's really just a motivating question rather than like what we are actually after solving. Yeah. So yeah, so if we do like the continuous time walk, what it does is that instead of just like sampling from the boundary of the set, it samples from this like smoother distribution, so it kind of just like smooths out the boundary more, and that's why it helps in this if you have a set that has very weird boundary, what like it tells us more about the length of the boundary of the set. Okay, so like if we take the 1 over delta steps random walk, then the total number of steps that we end up taking is a binomial distribution on delta. And if we take delta to 0, it's a fact that this converges to the Poisson distribution. And yeah, so at this point there's no real reason we needed to take like the time equals to 1 here. We could have taken any like continuous time parameter, and that's so we replace the 1 with some continuous parameter t, and that's called the continuous time random walk. Yeah, so like this has like this is a really special operator that I will spend like most of the rest of the talk talking about. And yeah, so it's called the heat operator. When we take the heat operator acting on the set, it splits out the distribution of what happens if you take a point and you take Poisson T random steps from that point, and then you check whether the end of the random walk is inside the set or not. Yeah, so I really alluded a little bit to how instead of sampling from one set, we can think of sampling from a density, which just says that if we are talking about the conductance of a set, it's like we are picking a point uniformly at random from inside the set and then stepping outside. But instead, I could have given you not just like a set with a uniform distribution, but like an actual distribution of the points you pick your starting point from. So a density is a function, a non-negative function that has expectation 1, and that defines a probability distribution on the cube. And yeah, so we can define the heat operator on densities as well, where again, it's just the interpretation of this is just you pick a point from the given starting density, and then you take Poisson T random steps, and you end out and you look at what's the value of the original density at that point after you take the steps. Right. Okay. So there's also yeah, I just want to remark that there's also another interpretation of the heat operator, which is that you can, instead of saying we do like a random walk, you can kind of do a random walk independently on each coordinate. So you take the input of the function, and then with some probability you keep it the same, and with some probability you re-randomize it, which is you pick a random number from -1 and 1 and set the input to that. So this is kind of like you add some noise to the input, and when the noisy input thing is called the noise operator, and the heat operator is essentially the same thing on the Boolean cube as the noise operator. Okay, so one thing that we can observe is that if you take time to be really long, then what happens is you're just doing a random walk for infinity time. So that converges to the constant function 1. And why does this so interesting? In Markov chain speak, this is saying that the uniform distribution is a stationary distribution of the Boolean cube. And yeah, so our question is actually how fast does this convergence happen? So how fast, when you take the smooth random walk, does it actually converge to the Boolean cube, the stationary distribution of the Boolean cube? Okay, so to try and answer that, we kind of need to think about how do we measure the distance to the uniform distribution. And I'll first talk about one measure of the distance, which is the L2 norm. When you take, it's the sum of the squared distances, this squared displacements at each of the coordinates, and if you take F to be a density, then what the L2 norm is just it essentially is the variance. We can also replace 2 with P at any of these points, and so we just have these are the LP norms, and the infinity norm is the maximum. Yeah, let's look at some examples of this. So if you take the uniform density, then its LP norm is 1 for every P. Whereas if you look at the indicator of one element, the P norm is 2 to the n over 2. The 2 norm is 2 to the n over 2, and the P norm is this thing here. So what this is kind of measuring is that, well, if you have a uniform density over one point, that density is extremely spiky. It has one one big spike of 2 to the n, and everything else is 0. So what the LP norm is measuring is how spiky is this other spike there. And we can also check this intuition with the indicator of a half space, which has half the values being 2 and half the values being 0. So this is like a non-constant function, but it's also not super spiky, and so all the LP norms are like kind of relatively small. So yeah, it's also a fact that like the P norm always increases as you increase P, and in fact it converges to the infinity norm, which is the maximum, because like in all of these cases, if you just take P to infinity, that P minus 1 over P becomes like 1, so it just converges to the max. Yeah, so we might hope for some statement of this form, which is just saying, if we have a function and we apply the heat operator to it, can we bound the maximum of the heat operator applied to the function after some time by the initial variance of the initial function? And turns out that we can't, because we can put up weird functions that breaks this for every time.
I'm sorry, could you just go through the calculation of why you got 2 to the n over 2 for the one element LP norm?
Okay, so well, I guess I can write it down like that. Hold on. Okay, I'll just say it once then. So you have one point that has 2 to the n on that point, and you square it, but then you need to take the expectation. So you divide by 2 to the n. So it's 2 to the 2n divided by 2 to the n, and then you take the square root of that. Okay. Yeah, so this is not true, but we can actually make another calculation that shows that the heat operator applied to a function, the 2 norm is always bounded by the original 2 norm of the function. And in math speak, this is H. The heat operator is a contraction of the 2 to 2 norm. It just says that it always makes distances smaller when you look at the variance of functions after you apply the heat operator. So we also know that the P norm actually converges to the infinity norm. So a reasonable question now to ask might be something like, can we, if we fix some reasonable number that's bigger than 2, 4, can we find some T that makes such that the heat operator applied to the function in the 4 norm is controlled by the variance of the function originally? And it turns out that, yeah, we actually can, and this is called the hypercontractive inequality, and that's why, so yeah, this 4 to 2 thing is why it's called hypercontractive, because it not only contracts when you go from the 2 norm to the 2 norm, it also contracts when you go from 2 norm to 4 norm, which is a bigger norm than the 2 norm. Yeah, any questions so far? Okay. Wait, okay. Yeah, so next we can talk a little bit about how to go about proving this. Yeah, well, so we can prove this hypercontractive inequality directly on the Boolean cube, but I'm not going to do that. I'm going to go through some other notions of distance to uniform, and then kind of indirectly prove hypercontractivity at the end of it. So yeah, so we look at some other measures of distance, which is one of which is this thing called the Dirichlet energy, which is also sometimes known as just energy or the average influence or the local variance. I think the local variance is an interesting name because it's, well, the L2 norm is the variance. So this is the energy is a local version of the L2 norm, because it's the L2 norm that samples from the edges on the Boolean cube, right? So this is, yeah, what this thing is saying is it's the expectation over, you pick a random edge, what's the difference of the function, the squared difference of the function on either end of the edge. The half here you can just kind of ignore because it's just a scaling factor that makes some things easier. All the constants in this talk are not super important. Yeah. Yeah, so let's plug in our favorite like indicator function of one variable and look at what happens. So when we plug in f equals to the indicator function or something, what we get is that like this thing is only non-zero if one end of the edge is inside and one end of the edge is outside. So it's just equal to the probability over random edge that one end is inside, one end is outside. And we can like condition on the probability that x is inside, and this is actually just equal to the conductance times the volume. And in particular, if you consider like A to be a set of like constant volume, then the energy is like a constant factor away from the conductance. And another like measure of closeness to uniform is this notion of like relative entropy, which is if you take the uniform distribution on the cube and probability density, then we define the KL divergence to be this just the expectation of phi ln phi over the uniform distribution. It's also equivalent in this case to the entropy of the density. Yeah, so we can relate these two notions of distances from uniform by this thing called the log-Sobolev inequality, which says that if you have a density and you look at the energy of the square root of the density, it's always going to be lower bounded by something times the KL divergence of the density to uniform. And on the Boolean cube, we know that this rho is like 1 over n. So,
On the previous slide, phi was a probability distribution.
So phi is a probability density, so it has like expectation 1. Yeah. Okay, so I'll talk about how we prove this inequality. Well, we can go by inducting on n. The n equals 1 case is like a kind of long calculation, but it's elementary. And when n is bigger than 1, then we just make the observation that if you fix one coordinate on the cube, then the rest of the cube is exactly just n minus 1 dimensional cube. So you can kind of just like condition on the last coordinate, and when and induct, and that gives you that proves the inequality. Yeah. So I actually like wrote down the proof of this thing exactly in the next 2 slides, but I don't think. Yeah, I'm not going to actually go over it. I'm just going to like say that it exists and it's indeed short. My point is just that once you have the idea of like conditioning on the last coordinate, and you just like write down some definitions, and you use this thing called the chain rule or the KL divergence, which says that if you have the KL divergence with some function, you can actually split it up into the marginal or the last coordinate and the restriction to the first like n minus 1 coordinates. And then that lets us use like n equals 1 case on the last one, and we use induction on the remaining one. And you just like write this down, and it's like that. So yeah, I'm not even going to say anything about this. It's like really short and easy. So yeah, now that we've proven that inequality, like let's see what happens if you try to substitute in the uniform like density over a set into this thing. So yeah, it looks kind of good, but once you if you just like write down the definitions and calculate, this is actually the energy of like the square root of the uniform density over a set is just equal to the conductance. And yeah, so this is essentially the same computation as like the indicator function one, except you have like a scaling factor because of this volume here. And then if you also write down the KL divergence of uniform density over set to the uniform distribution, then it's just like negative ln of the volume of the set. So if you put this together, we get this like very nice inequality that says that, well, if you have a subset of a Boolean cube, then the conductance is going to be lower bounded by this like 1 over n times the ln of 1 over volume. So like in particular, if you look at the indicator of one element, it's going to be approximately like omega 1. And if you look at the indicator of like a half space, then the conductance is like at least 1 over n. So yeah, like this, the point here is that these sets, like we've been thinking about these sets as like specific sets that like one element set and like the half space set. But this inequality is saying that for all sets of the same volume as these things, we have like we have a lower bound on the conductance. So in particular, if you look at the one element set and you look at like a constant number of elements in the set, it also has this like omega 1 conductance. And that's like actually really cool because it says that if we had only a constant number of elements to choose from, we can't pick a set. So we can't like choose the elements in the Boolean cube in such a way that a constant number of elements is going to give us like a low conductance. So like what I was talking about right at the beginning of the talk, it can't happen. But in the case that you do have like a large number of elements in the set, it's possible that the conductance can be relatively low. Like you might need to take n steps to get out of such a big set. And we can also kind of get some intuition about distributions from the indicator elements, because if you have a distribution, we can just kind of think of that as the indicator. It's like an indicator function of all the super spiky bits in the distribution. So if your distribution only has like a small amount of spiky parts, then it needs to like, if you do a random walk on that distribution, it needs to like spread out super quickly. But if you have like a distribution that's kind of flat, it could be that your random walk takes a while to converge. Yeah, so it also turns out that like the hypercontractivity that we were talking about is actually just like equivalent to this log-Sobolev inequality. The proof is kind of technical, so I won't go into it as well. It's basically we just like define a function that's the heat operator of f with like this norm that's like 1 plus e to the 2t, which is just like a number I picked out of my hat. And then you differentiate this function, like whatever that means, and somehow you can use the log-Sobolev inequality to show that this is always negative. And if you plug in 0 here, you just get the 2 norm of f. And it's also true that you can do the opposite, like you can also kind of integrate the equation to get the opposite implication. So yeah, like this like f prime being negative thing, it kind of tells us more than just the 4 norm being bounded by the 2 norm fact. It also says that if you have like any P norm, any Q norm here, it's going to be bounded by the 2 norm if you take like at least T is like, this is like n times the constant. So if you take like approximately n steps, you will almost mix like a function in the Q norm. Yeah, so in particular, if you plug in Q equals 4, then like this, you get like this, you can get the exact constant of n that you need to use. So yeah, there's also like a really short proof that can let you.
Sorry, this value for t to threshold is sharp. It's number n times log q minus 1 over 2. This is a sharp value.
I think so. Yeah.
And what's the extremizer? Or when is equality attained?
I don't know. Sorry. Yeah, so we can also, so here you have 2 on like the F side, but we can also like swap the places of like Q and Q by using a really short proof that involves Holder's inequality, and that tells you that if you have like if you take any Q and you find like the Holder conjugate, you can bound the 2 norm of HT of F. So why that's important is because if we plug in our indicator function example here, that will give us something pretty nice. Because the heat operator applied to indicator function has like a nice, the 2 norm of that has a combinatorial interpretation that's like the probability that you take one element inside the set, and then you do the random walk that the heat operator defines, and you do the random walk that's defined by the heat operator for like 2t time, and you check what's the probability that you remain inside the set. So, and on the other side of the inequality, we can also like plug in the indicator function, and that just pops out the volume of A raised to the 3/2 power. And yeah, so when we put that together, we get like another version of the small set expansion property, which says that if you have if you look at the random walk that I was talking about, the probability that you remain inside the set after taking like Poisson 2t steps is bounded above by the volume of the original set. So so when we and you can like rewrite this equation in this form as well. So that kind of says that the probability that if we pick like a random point inside our set and we take like n steps, then we're almost surely going to end up outside the set. If the set has like a constant volume. Yeah. So previously the other version of the small set expansion kind of said what happens if you have like a really small set, and this tells you what happens when you have like a slightly larger set. Like you can still get out of the set after taking steps that's drawn from this distribution. Okay, so here's what's been happening so far in this talk. We showed that the Boolean cube has a small set expansion property, and that's proven by hypercontractivity, and it's also equivalent to the log-Sobolev inequality. Yeah, so now I'll talk a bit about what applications hypercontractivity has. So yeah, we were saying if you look at the sets of volume of half, then that's going to be minimized by the dictator sets, like the sets that depend only on one coordinate. So our question now is that if you have a set that has conductance that's almost close to the minimizer, does it have to also look like a minimizer? And yeah, so we have to define what the minimizer actually, what it means to actually look like a dictator set. And to do that, we define this like notion of influence, which measures how much changing one coordinate has, how much influence changing one coordinate has on the output. So the influence is like the expected value of the squared difference of if you set the bit at coordinate I to 1 versus you set the bit at coordinate I to like 0. So if you think about the dictator set, then the influence is 1 at the coordinate is the dictator of, and it's 0 otherwise. and the energy is like the average influence. So yeah, the question that I was asking about, like, if you have a set that has almost minimizing conductance, does it look like a minimizer? Like, this is answered positively by the KKL theorem, which says, kind of qualitatively, it says that if you have a set that has volume, like there's constant volume, and the conductance is like at most a constant times the minimizer, then there has to be a coordinate with influence at least a constant. So yeah, the constant, this like influence at least a constant, you can think of it as being very large, because if the average influence is approximately equal to the average influence is just the energy, which is approximately equal to the conductance, which is 1 over n. So without like proving this theorem, you can imagine that the function actually has all the influences equal to like 1 over n. But this tells us that like that's not the case. Yeah, so it also like, yeah, so there are actually lots more applications, but I don't have time to go into them all. Maybe you can, so hypercontractivity also tells us some stuff about low degree functions, about like learning theory and social choice, the inapproximability of like, and there's some distributed computing applications as well. Yeah, so finally I'll get around to talking about non-product domains. So the proof of, when we were proving the log-Sobolev inequality earlier, we kind of used the independence of the coordinates very crucially. Like there was this bit where we had to condition on the last coordinate and notice that the rest of the cube looks, the rest of the coordinates look like a lower dimensional version of the cube, and we also use that like KL divergence statement. But there are lots of other Markov chains that don't have this product structure, and the question then is like, can we also show some sort of small set expansion property on those like non-product Markov chains? And yeah, so one of the closest like non-product domains to what we've seen so far is like a slice of the Boolean cube. That's like what it sounds like. We take one level of the Boolean cube that has a certain Hamming weight, and we call that a slice. And this has other names in the literature, such as the Johnson scheme. So I like to think about the elements of the slice as strings of length n with a fixed number of zeros and ones. So we also so we were talking about like doing a random walk on the slice. So in order to do that, we need to define what's a neighboring element. So like in this case, if you think about the Boolean cube case, we flip one bit. But in this case, flipping one bit is going to bring us to like a different size, because that changes the number of zeros and ones that are in the string. So instead of only flipping one bit, if we flip like a 0 to a 1, we need to flip another 1 back to a 0, or like vice versa. So that is equivalent to picking two coordinates and swapping them. And that's how we define like the neighboring elements on the slice. Yeah, so from that we can, so this is like a non-product domain, because now like the coordinates aren't like independent anymore, because once you know the first like n-1 coordinates, then once you know like the first, if the slice has like k zeros, and like you look at the coordinates and the first k coordinates are all like 0, once you see k zeros, you know that the rest of the coordinates all have to be 1. So that breaks the independence of the coordinates, and we can no longer just use the product domains like techniques. So this also, like, we can also look at different kinds of non-product domains. So for example, there's this like kind of algebraic structure called the Grassmann graph that was very used a lot in the recent proof of the 2-to-2 games conjecture. And we can also look at the Markov chain defined on the symmetric group and the multislice, which I'll just define now. So the symmetric group is like the group of all the permutations, and we can think of that as just like a string with like n different numbers. And again, if we define and usually we have the symmetric group acting on itself. So what that means is the neighboring element to one element of the symmetric group is actually just you take two elements and you swap them again. So it's actually very similar to the slice in this case, but instead of having the slice being you see two different elements in the symmetric group case, you see n different elements. So the next natural thing in between these two is instead of saying we have two different elements, what happens if we have three different elements? And still you can our notion of neighboring element is just to swap two different elements. So yeah, once we have this sort of non-product domains where the neighboring elements are defined by transpositions, we can also try to prove the log-Sobolev inequality on that, and that's going to give us the small set expansion, etc. properties that we really like on the Boolean cube. So on slices, it's been calculated that the inverse of the log-Sobolev constant is theta of n log n squared over k times n minus k. So
Can you define what is the inverse log-Sobolev constant is?
Right. So it's just the inverse of the log-Sobolev constant. Which you mean
But what does the meaning of that number? Sorry, I mean, so it's presumably constant in some inequality. Can you write down that inequality?
Oh, okay. I think it's somewhere. Okay, it's a lot of slides ago. Sorry. Okay. We can just. Did I skip it? Oh, did I? Oh, yeah. So it's this thing. Yeah. Sorry about that. It's So it's just the log-Sobolev inequality was we compared the energy and the KR divergence of.
So first, energy here is what you are doing. Picking a random element, you're making one step of your walk.
No, so the energy is we're picking a random edge and looking at the difference of the function on the two ends of the edge.
So edge means. So what edge means in those examples?
So in those examples, that's what I was talking about, neighboring elements. So from one element going to a neighboring element is connected by an edge. So on the slice, it's a transposition. You transpose two.
Okay, so you're line loops. You're line loops. And multiple edges.
Yeah.
Okay.
Right. Okay.
So when you pick in an edge, it means you pick two envelope vertices. And what does it mean picking an edge?
Sorry,
what does picking an edge mean?
It means.
Loops.
So you pick one point in the chain and you do one step from it.
Okay, so this is okay, fine.
Right. Yeah, so it does have subgroups, yeah.
Okay. Okay.
Okay.
Also, you mentioned the log-Sobolev thing is equivalent to hypercontractive inequalities.
Right.
And when you stated hypercontractive inequality, you didn't put a constant there in the inequality.
So it does. It's there actually, because if you look at the how do I?
So is it absorbed in T or something?
Yeah, it's in T. So okay, I can't find it anymore. Yeah, so it's right. There's this T thing has I wrote this on the cube, but actually this n here it comes from the log-Sobolev constant. So actually this T is log cube minus 1 over 2 times the log-Sobolev constant.
The log-Sobolev constant can depend on it.
Right, yeah. Yeah, so actually, like, that's why we were so, like, caught up with the log-Sobolev constant being n and not, like, n log n, because so it happens on the symmetric group that the log-Sobolev constant is, like, actually n log n. But the thing is that, like, the hypercontractivity doesn't work with the same parameters if you have n log n instead of n, and so that's why we can't get, like, say, the KKL theorem if you have the log-Sobolev constant being n log n instead of n. Okay, so so if you look at the slice with this log-Sobolev constant, then the k over if you look at k over n being a constant, then this is only a constant factor away from the log-Sobolev constant on the cube, and that gives us a lot of, like, nice things. Whereas people have also calculated the log-Sobolev constant for the symmetric group, and that's like n log n. So yeah, the middle, like, the point of this is that so this theta here means that, like, this is actually tight. We can find, like, if you look at just the indicator function of one point, then that function is going to have exactly this, like, log-Sobolev constant. Right. So yeah, the point of this is that, like, the middle slices in the Boolean slices, they have the same, like, expansion properties as the regular Boolean cube, and that's, like, very nice for us. We get a lot of, like, knowledge out of knowing that. And so our question is, like, does this also hold if you increase the number of, like, different coordinates in the slice? So if we look at like the multi-slice case where there are, like, 3 different colors, does it look more like the slice, or does it look more like the symmetric group? And it turns out that we show that if you have a multi-slice, then this is going to actually satisfy something that looks more like the slice than like the symmetric group, because if you take the inverse log-Sobolev constant, and you imagine all the n over k's to be, like, constant, then this is, like, basically like theta of n. And we can also show that, like, up to constants, this is tight, because if you again look at the indicator of, like, one element, that's going to if you have a slide that only has, like, one element of one color, that's going to look a lot more like the symmetric group than like the Boolean slice.
This is multi-slice with 3 symbols.
Yeah. So we can, of course, also generalize it to, like, a constant number of symbols, but I just wanted to keep the notation simple. Yes?
For this particular inequality, my attention is drawn in particular. So kappa 1, kappa 2, kappa 3 can be any positive numbers that satisfy that.
Right.
So is there, like, any meaningful interpretation in the sense that we set those to all be equal to each other, and sometimes you could combine the logarithm terms? Is that true?
But sorry, what do you mean? Like,
So,
well, they're like different colored elements.
okay, so I guess what I'm asking is there, like, a meaningful interpretation either in the heuristics of the problem or in the inequality itself if you set all the kappa i's to be equal? So in this case, kappa 1, kappa 2, kappa 3 all equaling n over 3.
I mean, I guess that's like the prototypical case that we want to consider. And in fact, like, from what we know of the lower bounds, we can't hope to get a good log-Sobolev constant if they are not, like, approximately equal.
Oh, okay.
So maybe I'm still confused. So if you have more than 3 colors,
Right.
if you have n colors and each of the kappa is 1, if I plug it in, if I get this expression, I'm going to get n squared times.
Right. So yeah, you do get, like, this n squared thing if you plug in n colors, but if you, like, open up the proof and, like, tweak some things in the recursion that we get, you can actually recover the symmetric group case as well. Okay, so yeah, I just said that if we consider the case where the multi-slice has, like, the same number of colors in each element, then we can get some small set expansion that's like has the same up to constant. It has the same expansion properties as the hypercube, and it also has like the various other like isoperimetry properties, like a version of the KKR theorem. So I'll just talk a bit about like what happens when you try to prove a log-Sobolev inequality on like non-product domain. So the first problem you face is that, well, it's not a product distribution, so you can't do the thing where you like where you just condition on one coordinate anymore. But okay, the KR divergence chain rule is still true, so we can still do this induction thing, but it's just a lot more complicated. And so yeah, like I was saying, we somehow only care about the case where the slices are like almost the same, the colors are almost the same size. So what if we just try to prove it for the slice where each of the colors are exactly n/3? Well, so like we said that we want to, but the only thing we know what to do with the KR divergence is like to induct it. So when you try to induct, you have to like pick one coordinate to delete, and that brings you to like a lower slice where the colors are no longer balanced. So even if you just want to know the result of the slices that have like equal elements, you end up having to show some bound for like every slice anyway.
Sorry, could I
Yeah.
for a second? So in the regular hypercontractivity case, the heat operator, it's a diagonal operator on the Fourier basis.
Right.
Right. Is there like, does it look nice even in this case?
In some sense, yes, because so we know some stuff about Fourier analysis on like the symmetric group. So you can still kind of decompose the heat operator into like bits that act on functions of like the same degree. And we actually do use that in like parts of
What's the basis for symmetry?
well, it's like the characters of like it's like the sorry.
What's the if you want to work the rest of symmetry? What's the basis?
It's like the wait, what is it called?
Irreducible representation.
Right. Yeah. Yeah, you look at like the irreducible representations, and then like what I was talking about just now was that like the heat operator breaks into different parts based on the degree of the function. So like that's what representations like break the basis into.
So it's still like a diagonal operator?
And it's like not in the same sense because like the irreducible representations have like different degrees now. Yeah. Okay. We can talk about that later. So yeah, and another like problem that we might encounter is that like in the two color case there are actually only two different types of transpositions. Like the ones that keep you at the same element and the ones that bring you to a different element. And if something brings you to a different element, then it must swap like a 0 and a 1. But on like the three color case, you could swap like a 1 and a 2 or a 0 and a 1, and we don't know like which case we should consider. Yeah, so these are like kind of just the problems that we face when we try to prove it on non-product domains, and because I have no more time, I'm just going to leave it at that. And yeah, so the summary of what I've been talking about is that like the Boolean cubes have a nice small set expansion property, and it's like implied by the log-Sobolev inequality and hypercontractivity, which are equivalent to each other. And we can also, with like some amount of work, extend this to non-product domains and get similar like extension properties there.
Why do you look at multislice? If number of cards is true, then it's basically you do a random hemisphere. But if you go from that Q to that Q, it's not a hemisphere, it's really a multislice. Right? So,
it's kind of just to understand better like the different kinds of non-product domains there are. Because like, I mean, we understand one end of the spectrum, which is the slice, and the other end is like the symmetric group. So it's like looking at things in the middle.
There are no more questions. Let's take